In this tutorial, we'll be going through CCMAC, where CC stands for Correlation Based Collaborative MAC. In a spatially dense sensor deployment application, the sensor records may be spatially correlated subject to an event, because closely spaced nodes will all be capturing the same event, so thereby all their values will be similar. So that is why that part is exploited over here. That is, exploiting spatial correlation in the context of collaborative nature can lead to significant performance improvement in communication protocols. Spatial correlation model. So let's see how exactly this entire thing can be modeled. Sync is interesting in observing physical phenomena using the observations from multiple sensor nodes with highest accuracy. So sync can be thought of as ultimate node, that which receives all the fused information. So this sync is very much interested in observing physical phenomena or any event that which is happening from multiple sensor nodes with highest accuracy. Physical phenomena here is modeled as spatio-temporal process given as S, that which is a function of time, as well as spatial coordinates x and y. And here we are assuming that there are n number of sensors in the event area. Observations of a subset of m sensor nodes will be taken into consideration. That is, we are trying to consider a subset of containing m number of sensors that which is lesser than or equal to n. Sensor node Ni observes. So this observation done by a sensor node Ni can be thought of as Xin, that which is a noisy version of the event information capital S subscript I of n. So this is the actual information, and because it is getting captured by some sensor node, that too under the influence of the environment, that which involves noise in it. So this is the noisy version of the same information represented as X. Observation is then encoded in the form of Yin. So all those observed observations are in turn encoded as Yin, and ultimately this Yin will be transmitted to the sync of wireless sensor network. The sync at the other end decodes this information Yin in order to estimate the actual event information S. So here it's S cat. So these are all the important equation that which we are supposed to assume. So here the mean value of this S is assumed to be 0, and the variance of Si is given as this, followed by covariance of Si and Sj is in turn related to correlation in this fashion. So this covariance is in turn equal to correlation into variance, and if I cross multiply this variance onto the left hand side, we will get correlation of Sij in turn equal to this covariance can be thought of as expected value of Si into Sj divided by variance. So for here, Dij can be thought of as distance between the node Ni and Nj located in coordinates Si and Sj, each observed sample Xi of the sensor Ni. So where this is the variance of the event information Xi, Si and observation noise Ni. So in fact this Xi is the noisy version of the actual event Si. So Si plus Ni is the noisy observed version. So this is in turn encoded as Y, and Yi is sent to the sync, and over the sync it will be read as Zi in turn equal to. So here we got to repeat the same expression, but the only change is here Sj is replaced by yi and multiplied with yi. Accordingly, estimate of S is given as mean. So this is the the average value that which we are trying to calculate, because initially we had considered a subset of the entire sensor node M. So here we are trying to calculate the average value. So we got to divide it by M by adding all these received data. By adding all the received data Zi and ultimately dividing it by M, we will in turn get an estimate of S. So this is the concept of spatial correlation model. And for all of this to happen, here CCMAC operation involves iterative node selection algorithm, INS, and distributed CCMAC protocol. So this iterative node selection algorithm runs at the sink, whereas distributed CCMAC protocol runs over the node. So first INS algorithm will run and it calculates a value called as R correlation, that which will be in turn sent to the nodes, and in turn nodes will make use of this distributed CCMAC protocol involving R cross correlation, R correlation. So here redundancy in the network allows a sensor node to act as a representative node for several other nodes in its vicinity. These nodes are referred to as correlation neighbors. As a result, from the standpoint of sink, it would be enough for only one node, that is representative node, to send its information. Correlation region, the area where the representative node and its correlation neighbors reside. So CCMAC operation is based on the operation of two entities. One is INS and the other one is distributed CCMAC protocol. So let's first go through this INS, that is iterative node selection. INS algorithm resides at the sink to determine the operating parameter of the distributed CCMAC protocol. Statistical properties of WSN topology are used as input. So as input will be feeding in network density and variance value of this topology. INS algorithm provides the average correlation radius, R correlation, between the nodes. The minimum number of representative nodes is given by this expression. So because we are trying to consider a subset of N, that which is represented as capital M, so this has to be always be lesser than D max, and it's given as argmin of DEM lesser than D max. So where D max is maximum distortion allowed by the sensor application. So this is the maximum distortion allowed by the sensor application, and this DEM has to be always be lesser than the maximum value. The calculation of the correlation radius consists of three steps. One is vector quantization technique. By using this vector quantization technique, it forms Voronoi regions. So these are all the Voronoi regions that looks like a farmland. So this is the first step while calculating R-core. The second operation involved is average distance between the center of these Voronoi regions are used as the correlation radius. The average distance between the centers of these Voronoi regions are used as the correlation radius. The average distance, that is D average, between the representative nodes is found where D average is equal to 2 times that of R correlation. So if I compare any two Voronoi regions, so it will be equal to 2 times that of R core. So this is the representation of nodes and Voronoi regions. So here we just went through the procedures which were involved in iterative node selection, followed by how exactly this R core is actually calculated. Then it makes use of CCMAC protocol at the nodes. CCMAC operation is performed through two components. The very first one is EMAC, where E stands for event, followed by NMAC, where N stands for network. So back in EMAC, correlation in the region where an event occurs is handled by this EMAC, and NMAC handles route through packet. Event MAC is initiated by first contention phase, abbreviated as FCP, where nodes in close proximity to each other contend to become a representative node using four-way handshaking signal. So basically in this first contention phase, where nodes in the close proximity to each other contend to become a representative node, then each of these nodes sets the first hop field of the RTS request to send a packet and tries to capture the entire medium for transmission. Node Ni captures the channel after the first contention phase. It becomes a representative node of the area determined by the correlation radius R core. Every other node Ni then listens to the request to transmit packet of the node Ni. If the node is outside the correlation region of node Ni, then it contends for the medium. Operation constructs, and this operation constructs correlation clusters. So we were having virtual clusters in SMAC, but here we are having correlation clusters, and these correlation clusters are mainly because of R core, followed by first contention phase. So after formation of correlation clusters, and let's see how exactly data packet is routed to the sink. Packets from these regions are handled by network MAC. Relay nodes clear the FH bit. So relay nodes are the nodes which are between the actual sensing node and the sink. So that which connects all the way to the sink are called as relay nodes. So these relay nodes clear the FH bit. So where FH is first bit which was earlier set in the RTS packet, but these relay nodes will clear that FH bit on receiving a packet and relay it to indicate that the transmitted packet is a route through packet, and it's not because of that node sensing. So because here importance should be given to the previous value which has already been measured. So this node with the route through packet listens to the channel for a time which is smaller than the DCF interframe space. Used by the nodes performing EMAC. So thereby this is getting precedence over here. So router node uses a smaller backoff window which is lesser than the size of the value used by the representative node. So thereby ultimately the route through packet is given precedence. And if you were to do this qualitative evaluation of this CCMAC, which stands for correlation based collaborative MAC, has several advantages, and let's go through those advantages one by one. So energy efficiency is increased by restricting the communication attempts to only representative nodes. Local contentions are minimized in this case. The EMAC and NMAC components of CCMAC provide priority to the filtered traffic and not for the current traffic that which is getting generated. CCMAC moves, and this is happening because of this DIFS, that which is of shorter duration. That which is happening due to a smaller time compared to that of DIFS. CCMAC moves most of the complexity to the sink over here, where computation hungry INS algorithm is run. Because of this INS algorithm, we'll be estimating the actual event signaling event that which was happening, as well as determining arc or entire all of these algorithms happen at INS, that is at the sink end. At the sensor node, the distributed protocol is implemented, which accepts only the correlation radius (R-core) as a parameter from the sink. The disadvantages of the CCMAC are it is applicable to a network where spatial correlation is dominant. That is, similar values should be associated with a cluster of correlation cluster over the entire correlation cluster. Each of those nodes should have same values. Only then this can work. CCMAC may not provide high savings if nodes observe independent data. If the data are not similar and if the data are independent of each other, this might not work. Locational knowledge of the neighbor for correlation is required, and thereby onboard GPS might be required, that which is an additional component. So these are all the drawbacks of CCMAC, and in order to illustrate how exactly CCMAC works, here is a diagram where you can see these are all the correlation regions. These are all the correlation regions that which is containing a coordinator, and this coordinator in turn receives the data from all these neighbors, and it routes that data through the relay nodes all the way to the sink. So this is the sink. So here it makes use of EMAC at the correlation cluster. It makes use of EMAC, that is event MAC, and whereas it makes use of NMAC in order to route the packet, that is network MAC. So here this thing represents the representative node, and these nodes are correlation neighbors. This is about CC MAC, and next we have hybrid MAC, and we'll be going through that in our next video.